All right. Hello, everybody. It's so great to see everyone. I see some familiar faces in the audience. Kaylee, where do we have people tuning in from today? Any interesting or exotic places?
Well, we have plenty of folks tuning in from Berkeley, Danville, San Francisco, Fremont, all around the wonderful Bay Area. I see someone from New Hampshire and another person from New Jersey. So thank you for joining us as a way to close out your evening. Um, Someone from North Lake Tahoe. I hope you're staying safe inside and not getting too smoky right now. Thank you for joining us. And excitingly, I see someone from Perth in Western Australia. So I'm not sure what
Whoa.
time it is there. You might be starting your day with us. If I think I'm doing the math right.
Well, welcome everybody near and far. Thank you so much. I'm so happy to have you. This is our last summertime lecture. We are ending the summer out. Even though classes have just started at UC Berkeley, but we're starting with Harriet Lau. We're closing out with what can studying tiny vibrations deep within the earth teach us about our planet? And now that we know that most of our folks are tuning in from the Bay Area and from afar, I would like to start today by giving our land acknowledgement. So UC Berkeley and Science at Cal recognize that Berkeley sits on the Huchun territory, the ancestral and unceded land of the Ohlone people, the successors of the historic and sovereign Verona Band of Alameda County. This land was and continues to be of great importance to the Ohlone tribe and other familial descendants of the Verona Band. Every member of the Berkeley community has and continues to benefit from the use and occupation of this land since the institution's founding in 1868. By offering this land acknowledgement, the Berkeley community not only recognizes the history of the land on which we stand, but also recognizes that the Ohlone people are alive and flourishing members of the Berkeley and broader Bay Area communities today. So thank you for allowing me to take the time to give that acknowledgement. As most of you may know, and if you don't, you are new to the Science at Cal community. Science at Cal brings the wonders and the excitement of UC Berkeley STEM research to the community. Of course, all of our events and programs are free and geared towards public audiences. So we are happy to have you here time and time again. Typically, we are in cafes, in lecture halls, at festivals. We're at Cal Day. We partner at First Friday events. We're at farmers markets. We're all over the place. And that's how we like to be. Unfortunately, as you know, because of the pandemic, we are now virtual. We will probably continue to be virtual a little bit longer as we try to ride through this Delta variant, but we hope to see you very soon in the fall. So thank you for continuing to show up to our virtual events and supporting Science at Cal. We want to thank everyone for donating today. Of course, thanking our advisory council, thanking our home at the Lawrence Hall of Science, and thank you again to all of you who have participated in our programs in the past. I'm going to now hand things over to Harriet, and while I do, I'll stop sharing. I do want to mention that we want to save some bandwidth, so if you can turn off your camera if you'd like. Keep yourself muted, but we will give you a chance to actually unmute yourself at the end of the event today, at the end of Harriet's presentation. We can do some Q&A time with her, and you can, again, like I said, go ahead and unmute yourself and ask those questions. So to do that, you're going to go, and at the bottom of your Zoom screen, you'll see the reactions button. You're going to click reactions, and then you're going to raise your hand. And then I'll go ahead and call on you, and we'll be able to unmute. For those of you who don't want to save your questions till the end and you'd rather me ask the questions, we love a lively Q&A. Go ahead and continue to ask your questions in the chat box throughout the entire presentation, and I will go ahead and ask Harriet your questions for you if you'd like. So now I'm just going to go ahead and give a brief intro. Before joining the faculty in the Department of Earth and Planetary Sciences at UC Berkeley, Dr. Lau completed her undergraduate and doctoral degrees at Imperial College London and Harvard University, respectively. Her research involves exploring global scale geodynamical problems across many time scales, including the solid Earth and the ocean tides, acting either in hours all the way to years, and the formation of the Earth due to the melting of large ice sheets. The deformation, not the formation, the deformation of the Earth due to melting large ice sheets from also years to tens of thousands of years. And mantle convection, which I'm sure she'll hit, the process that drives plate tectonics, again, from millions to billions of years. So she's thinking about timescales anywhere from hours to billions of years, folks. The theme of all of this work is to understand how we can coherently characterize Earth's behavior across vastly different timescales. So I am already so excited to hear your talk, Harriet. I've already told Harriet I have my undergraduate degree and PhD in Earth and Planetary Sciences. So this is a treat for me to be able to share the stage and introduce Dr. Harriet Lau. So please take it away.
Thank you, Dee. I guess I've got to live up to your excitement now. Good evening, everyone, or good morning, I guess, for some of you. And thanks for tuning in to the event. And thank you for the organizers for asking me to speak today. I'm really grateful that you all have taken time out of your evening to listen to me talk about my research. So I'm a theoretical geophysicist. So that opening slide with me out seeing the beautiful Rocky Mountains out in Canada was just for fun and nothing to do with the actual work I do. I'm actually useless in the field. I can't read a map to save my life. And so today I'll be focusing on perhaps quite an underappreciated physical process that we call earth tides. But in particular, what this kind of mode of vibration can teach us about the deepest parts of the earth. And so by the deepest part, I mean our mantle and mantle dynamics. But what exactly do I mean by these words? And so if we take a slice of the earth through depth, this is kind of what it looks like. What we have is an iron core, solid on the inside, and it's wrapped and surrounded by a liquid iron shell. The mantle, which is really the focus of today's talk, is basically 3,000 kilometers of solid rock beneath our feet. And finally, on the surface where we all live, we have the crust, which is this green tiny line here. This is a photo of a smilodon. This is a statue right in front of the building on campus where I teach. Apparently smilodons, if I talk to my colleague, paleontological colleagues, they roamed California around tens of thousands to hundreds of thousands of years ago. And so it's the saber-toothed tiger. It's the state fossil of California. But anyway, what happens in the mantle is that the base of the mantle is being heated from energy being released from the core. And at the surface of the earth, we're being cooled by space. And so this is what happens. You have this kind of motion, right? Remember, the mantle is solid, not fluid. But over really long time scales, it flows. And this motion is about the same speed as at the rate at which your fingernail grows. So it's really slow. If you heat up rock, as we're doing at the base of the mantle, the rock expands. And so it becomes less dense. And so it floats. On the other side of the mantle, at the top, you're cooling the rock. And so it contracts and becomes denser than average and thus sinks. And that basically drives this flow that we're seeing here in this video. And it's really this type of motion we want to understand, because how this rock flows governs many processes on the earth. And so, for example, this tiny hot upwelling here, when it reaches the surface, might cause copious amounts of volcanism. If we look at places like this, these dark places where we have rock sinking and colliding, we either could form mountains or we could cause earthquakes, right? And so what drives this motion is extremely important. And we call this motion mantle convection, and it drives plate tectonics. And if you remember in perhaps your high school geography class, the Earth's surface is broken up into several plates. And really it is the convective flow underneath from the mantle that drives the relative motion of these plates. And so, for example, if you're calling from California, we know that fault dear to our hearts, the San Andreas Fault. And if you're kind of even more local, if you're Berkeley, there's a little splay off that called the Hayward Fault that runs right through our stadium. These forces drive the stress that builds upon those plates that eventually, when released, will cause an earthquake, right? And so for the San Andreas Fault, we have the Pacific Plate and the North American Plate moving past each other, right? Fortunately, another place close to my heart, as you can probably recognize from my accent, is Manchester, really far from a plate boundary. So we don't have to deal with the threat of an earthquake. We just have really bad weather. All right. And so to understand this flow, there are two important parameters that we need to know about the mantle. The first one is the buoyancy, right? And this really just governs whether material is going to sink or if it's going to rise. And a good way to visualize this is if you just look at this little video of a lava lamp. I guess if you're an 80s person, you might have one of these stowed away somewhere. But ultimately, what this lamp is doing is heating this fluid from the bottom and cooling it from the top. And it drives this motion just as it does the same physics in the mantle. So as you heat the blob up, it expands, it becomes less dense, and it's going to rise. And so really, this is kind of what we need to understand. We need to understand the buoyancy of the mantle. Another really important parameter that I won't touch on today, but it's really a big part of my research, is the viscosity of the mantle. And so really what the viscosity is the measure of a material's resistance to flow. So if you look here, water is very runny, so it has a very low viscosity. It doesn't resist flow. Honey has a slightly bigger viscosity. And finally, if you think about tarmac or asphalt, has a very high viscosity. It's really hard to make tarmac flow. And really, because of this resistance to flow, when we think about the mantle, viscosity really governs the kind of length scales and the time scales of that flow. And just to give you a little bit of an idea of the relative viscosities of all these things, water has a viscosity of 0.001 Pascal seconds. Pascal seconds is the unit of viscosity. Honey has about 10. And so tarmac has about 10 billion Pascal seconds for its viscosity. I would ask you to guess the mantle values, but I guess with Zoom, there's a lot of awkward silence. So I'm not going to put myself through that misery. I'm just going to give you the answer. There are 22 zeros after the 10 in front of the mantle for the mantle value. So 10 to the 22 Pascal seconds. So the mantle is flowing, but it's flowing very slowly. All right. Okay. So what do we actually know about the mantle, that 3,000 kilometers of rock beneath our feet? So we got to ask, I'm going to kind of add some context here. There are two ways in which we kind of figure out what's going on in the mantle. We can either pick up rocks that we know have erupted from deep within the Earth's interior and do some chemical analysis of them, or we can do something called geophysical imaging. And we're going to go into both of these briefly, just to really paint a picture about what we know about the mantle. And so if we first look at the chemistry, there are two types of places we get mantle rocks from: the mid-ocean ridge and ocean island basalts, right? And so the volcanism at these two places are what we call basalts. And this is a map of the Earth's topography, so how the elevation of the Earth. And if we just kind of focus on these really light blue lines, you see these lines that traverse the ocean floor. These are mid-ocean ridges, and they curve basically at the edge of plates, where plates are moving apart. And when you move apart, you basically make a void, which allows new material to be formed in the form of volcanism, right? And so that new crust that erupts comes from the mantle. And so this is a cross-section of a mid-ocean ridge. So as the plates are moving apart, there's some cracks that you see. New material will erupt through that void. And this is what it looks like in the ocean floor, right? So we don't actually know what the depths of the ocean look like that well. It's actually really hard to get down there. But this is an image taken of the kinds of basalt that would erupt underneath the ocean. All right. So the other way we get kind of hints of mantle are through ocean island basalts. And so if you're lucky enough, these just happen to be some of the best places to do field work. So volcanic islands like Hawaii, like the Galapagos, Reunion Island. If you're someone that studies ocean island basalts, you've got the best kind of deal when it comes to visiting really beautiful places. And so the difference with ocean island basalts is that these volcanic islands, as you can see, they're these kind of orange spots here, they're not at all related to plate boundaries, not like the mid-ocean ridges that are essentially plate boundaries. Ocean islands can happen anywhere, right? We also call them hotspots. And so if we take a cross-section of ocean islands and what we think is happening underneath them, right, this is throughout the entire mantle. So this is the core, that metal iron kind of sphere. Then this is the mantle. And what we think is happening at ocean islands is that we have hot upwellings rising right from the base of the mantle, traversing 3,000 kilometers of the mantle, hitting the base of the crust and causing that volcanism that erupts to produce these islands. So the islands themselves are just made of piles and piles of basalt. And so this is the kind of eruption you might expect. So this is Kilauea in 1983, and I'm sure quite a few of you, if you've been fortunate enough to travel during COVID, Hawaii is one of the places people are hitting up. Although they don't really want us to come anymore. That's the latest I've heard. All right. And so just to bring these two together, these are the two sources I've mentioned. So we have mantle rock coming from mid-ocean ridges and mantle rock coming from ocean islands. And just to see here, this kind of schematic puts it well. Really, mid-ocean ridges tap the kind of uppermost part of the mantle, whereas ocean islands really source the mantle from deep within, right at the base, right? And we use these two types of basalts to analyze the composition of the mantle. And so what do we see? So in general, in the mid-ocean ridges, that chain of underwater volcanoes, the chemical analyses show that they're extremely homogeneous, suggesting that that shallow region of the mantle here, tapped by these mid-ocean ridge basalts, is generally really well mixed. In contrast, if we look at the ocean island basalts, the composition here is extremely variable. Some analysis suggests that there's material as old as the age of the Earth, so billions of years. And so when we think about mantle convection, a mantle that's overturning all the time, like the video I showed you, there's some material that has only seen the light of day today. It took 4 billion years for that piece of material to finally erupt at the surface, and it had never erupted before. And so just to summarize, from the chemistry, we have two basic conclusions. Near the surface of the mantle, mid-ocean ridges give a hint of a really well-mixed, homogeneous mantle. Whereas ocean islands, the basalts that are up there seem to indicate that the deepest parts of the mantle, there could be multiple reservoirs because the ocean island basalt composition is really heterogeneous. And so there are chemically distinct reservoirs, some of them extremely old. But the problem with the chemistry of these rocks is that, you know, we only get glimpses of different spots at the surface, and they really don't give us an idea of the geometry, right? So be it the spatial distribution or the volume of these different reservoirs. And so just to emphasize that point, many conceptual pictures of that compositional variation of the mantle have been proposed over the past decades, and here are just a few of them, and they all look totally different, and yet they all satisfy those chemical observations I listed. And so this is really where we turn to geophysical imaging, right? And so the most common way to image the Earth's interior is known as seismic tomography. And it's essentially taking a CAT scan through the Earth. And so here are some of these images of the mantle that have been made using this technique. And so let's think about a CAT scan. Here's me, a blue me, ready to have my CAT scan taken. And so what you have is you have a source of light waves in the form of X-rays, and they beam across you. And those X-rays enter your body and come out the other side, right? Right here where these detectors are. Now, different parts of your body, bones, flesh, what you had for dinner, will slow or speed up these X-rays as they pass through your body. And it makes each X-ray arrive at the detector at different times. And so with some very clever maths, you can use those different travel times to then compose an image of your body. And so this is, I don't know, I just pulled it up. I tried to pull something up a little bit more interesting, but this is someone's brain made from a CAT scan, right? And so what is the analogy for Earth? So it's basically the same math and the similar physics, right? So whenever there's a really big earthquake, seismic waves propagate throughout the entire planet. And the time it takes these seismic waves to propagate through the Earth and for a seismic station to measure that time, we get many of these different paths, many different travel times. And that tells you something about the material that seismic wave has traveled through, right? And so here are those CAT scans of the Earth dating back to the 80s. And so this is one of the earliest. Over time, these images have improved with better and better resolution, basically with bigger computers and more seismic stations dotted around the planet. And so here are just several examples of what these seismic tomography images, CAT scans of the Earth, look like at really the deepest part of the mantle. This is one of the latest ones, right? These are kind of, rather than kind of map view, this is a cross section, and this kind of cut out here is the core. And so what I'm showing you here in all these images, these blue and reds, this is the mantle's wave speed. So where blue, you see blue, these are regions in the mantle where seismic waves are sped up. The regions where they're red, seismic waves are slowed down. And I just wanted to highlight this latest one here. This comes from Professor Romanowitz's research group here at Cal. And Barbara, she is really one of the pioneers of this field. And so I'm very fortunate to have her as a colleague. But really, ultimately, these variations in wave speed, whether seismic waves are slowed or sped up through the Earth, tell us really important information about the physical state of the Earth. So for example, the temperature, the density, the composition, all of these things will affect the speed at which a seismic wave travels through the Earth. And so two common features to all of these images are what we call, it's a mouthful, large, low velocity provinces. And it's not named not for particularly subtle reasons. They're large, these provinces. I'm going to talk about them in a second. And they slow seismic waves as waves pass through them. So we call them LLVPs. And so here's a tomographic image at the base of the mantle. Again, blue highlights these fast regions. And these dome-like structures highlighted here, these are these LLVPs. One's beneath Africa and one's beneath the Pacific. And they rise to around 1,000 kilometers above the base of the mantle. So these are ginormous. And because they seem to lie beneath ocean islands, one could ask whether these are the prime candidates for storing that compositional heterogeneity that we see in ocean island basalts. Or are these just really just hot features in the mantle? Remember, hot could also slow down seismic waves. And just to kind of bring you a better image of these, this is another view of these structures, right? This is a seismic tomography image that really just captures kind of it across Antarctica, if you can see, and you see these two domes, right, emanating at the equator. This is the Pacific LLVP, and this is the African LLVP. And really, we have to think about these seismic tomographic images as snapshots in time. This is just what the mantle looks like today. It tells us nothing about evolution. It tells us nothing about the past, and it tells us nothing about where we're going, right? This is just a snapshot in Earth's kind of briefest moment in time. Remember, we have an Earth that's 4.5 billion years old, right? And so given the dominance that these LVPs have in the mantle, the physical source of what's causing seismic waves to slow down here really governs the energetics of mantle convection, and so holds really important implications for the long-term evolution of the Earth system in general and for plate tectonics. And so what we really need to know, and this comes back right to that original point, is what the buoyancy of these structures is, whether they're sinking or they're rising. And so this isn't really straightforward. It sounds like it should be, but you can either slow down seismic waves in two ways. You can either heat rock up, and that makes these LVPs light, right? They're going to expand and they're going to want to rise. Or you can enrich these LVPs in iron. And iron is a really heavy metal, and that would actually make these LVPs dense. Both of these processes will slow down seismic waves, but both lead to very different pictures of mantle convection, right? One in which it's very energetic, we've got hot upwellings, or one where these kind of dome-like structures are really sluggish and just don't want to do anything. All right, and so how are we going to get this? This is where this little known process called earth tides or body tides known, and a big part of my research is studying this phenomenon. And so what are body tides? Body tides are the deformation of the solid Earth under periodic stresses from the sun and moon. Okay, so just like ocean tides, right? If you imagine, you're at a beach, waves lap on and off the coast twice a day. And the reason why they do that is because the moon's gravitational pull deforms the ocean surface. So if you look at the Earth from far from space, the ocean surface is being warped by the gravitational pull of the moon. But it turns out that same gravitational pull also deforms the solid Earth. And so check this out. In California and in many parts of North America, we move up and down twice a day by about 40 centimeters. Fasten your seatbelts. Every 12 hours, we're going up and down 40 centimeters. It makes me feel nauseous. Okay, but what does that deformation look like? So this is really fancy animation by my standards. And so this is the Earth. Here's the moon and the sun. And under their gravitational attraction, this is what happens. The Earth just warps like this twice a day. It does this. And it just so happens that a key characteristic of the body tides is that makes them so ideal for investigating the LVPs is that they're really sensitive to deep mantle density structure. All right. And so let's talk about a very brief history on body tide research. I'm a big fan of scientific history, so I always have some element of this in my talks. And so body tides are really a problem where classical physics meets classical geophysics, right? And so as always with classical physics, starts off with Newton. Newton was the first to establish the theoretical framework in his theory of gravitation. Then there was some seminal contributions from mathematicians like Bernoulli, Euler, Maclaurin. Don't ask me which Bernoulli, there were like 12 of them. And then later on, kind of more classical geophysicists like Lord Kelvin and Darwin, George Darwin, not the famous Charles Darwin. George was famous too, if you're into geophysics. They kind of were the first to really develop a theory that actually describes how a sphere would deform under a tidal stress. And then eventually, a theoretical geophysicist called Love derived a body tide theory that is actually still used today, and we now call it Love number theory, named after him. I don't think he named it that himself. And then eventually, in more recent times, extensions to this love number theory were added to account for kind of more complexities in our planet. And I just wanted to highlight a mentor of mine, the late Professor John Moore, who was a geophysicist at Colorado. He really had profound insight into many topics in theoretical geophysics, and also had a lot of generosity. And I benefited a lot from that as a young scientist. And then finally, I certainly don't fit in when it comes to kind of scientific contributions, and probably other reasons in this kind of photo. But here's me trying to figure out tides by squeezing a deflated soccer ball. And if nothing else, I like the slide because it kind of shows the evolution of facial and, I guess, head hair in the European gentry. And I really do think we kind of peaked at love. Look at that mustache. What a mustache. Anyway, all right. So if you theoretically predict that the solid Earth is moving, you might want to observe it, right? Especially when it's as slow as 12 hours a day. It's really hard to get this going. Obviously, sometimes science happens the other way around. You observe something, then want to explain it. The body tides was the opposite, right? And so in the late 1800s, George Darwin, that same George that I showed you a photo of, set out to build devices known as tilt meters to measure the body tides. But his efforts proved to be in vain, and he exclaimed, "The measurements of Earth tides must remain forever impossible." He probably just mumbled it, but I like to think he really cried it in despair. I actually have a side theory as to why this didn't work. His work was mainly done at what's the now kind of discontinued Bidston Observatory, which is in Liverpool. And people from Liverpool don't get along with people from Manchester. I'm from Manchester. And so I am 99% sure that being in Liverpool, this was just a subpar observatory. All right. And so I did some more reading early on in my scientific career, and came across this quote from a really famous geophysicist who spent much of his career on body tides. And what he said was that the tides provide little information on Earth structure helps to explain why Earth tide studies have recently been a backwater of geophysics, albeit one in which a few of us have enjoyed paddling about. And so as a young scientist about to embark on a project in Earth tide, you don't want to hear that it's the backwaters of geophysics, but the backwaters haven't been too awful. All right. And so finally, body tides received the much deserved attention. The top 4 hit on Reddit on the 7th of April, 2016. All right. So when it comes to measuring body tides now in the 1900s, we do owe a lot of credit to places like the Royal Observatory of Belgium and scientists such as Dehaene and Melchior. They really dedicated a lot of their careers to observing this. And what do I mean? What do these observatories do? So what a lot of it involves is space-based technology, right? And so in the early 60s, how we measured this body tide was kind of indirect. It would be through perturbations to how satellites orbited the planet. These tiny perturbations would basically be affected by these body tides. Very long in baseline interferometry, I can't even say that word now, VLBI in the 80s, directly measured the crustal deformation, and so did GPS. And so thankfully, for my sake, at least for my research, George Darwin saying that measuring the body tide was impossible was just being a bit of a drama queen. All right. And so the data I use will come from GPS. And so we're going to talk a little bit about GPS and how that works. And really, it really is the same technology that you have in your phone that tells you where you are, right? And so GPS, the global positioning system, it is actually involves a network of about 31 satellites that orbit above our heads. In our phones, we have a GPS receiver that sends signals up and down to these satellites. And again, using that time taken for these light waves to travel, that you can get an estimate. You basically use triangulation to get an estimate of where you are. And so what geophysicists do is track the location of the Earth's crust as it moves due to processes like plate tectonics and, for the purposes of this talk, the body tide, right? And so our receivers aren't phones. They're these bizarre looking structures stuck permanently to the ground, constantly sending signals and receiving signals from that GPS satellite network. And so recently, a global GPS study published a data set consisting of this crustal deformation due to the body tides. And so this figure shows the difference in vertical amplitude of that crustal deformation. So we've got GPS stations all over the globe measuring this deformation, right? And so really the main take home here is that this study was able to get sub-millimeter level precision of these measurements, which is extremely impressive. And what they see is this very geographical variation in this crustal deformation. And what we really want to know is, what is the cause of this geographical deformation? And so what could be the sources, right? We're going to talk about each of these briefly, but ultimately what we're interested in that would cause this variation is that we have heterogeneous buoyancy structure in the mantle. And that is what we're interested in learning about, using this data set to teach us about this buoyancy structure in the mantle. And so what we'd like to do is apply our techniques to the data. We have to get rid of those other signals. So the ocean tidal loading, right? All this is the ocean tides that we are very familiar with. So if you're on a beach, the tides go up and down. That additional kind of redistribution of mass loads the Earth and deforms the crust, believe it or not. And so we want to get rid of that. There's boundary on the crust. So as the crust goes up and down, we want to get rid of that. Turns out there's also boundary at the core mantle boundary. There's undulations that we also get rid of. And so after all these corrections, what we're left with is the heterogeneous buoyancy structure in the mantle that causes this geographical variation in our GPS data. And so what we do is we're going to use this GPS data and update the theory, which we're going to talk about in a second, to determine the density distribution of that deep mantle. And so remember, the key mystery we're trying to get at is, what is the buoyancy of these LLVPs, right? So that is the motivation behind all of this. And so I am a theoretician. I don't really do much field work, which is sad. I like going outside. I just can't really do science outside, apparently. So what we're going to use is something called normal mode theory. And what are normal modes? These are normal modes in a very simple example. Like, take a string, like a guitar, anything like this, pinned at both sides. If you pluck a guitar string, it will resonate at distinct frequencies and wavelengths intrinsic to the guitar strings. And these vibrations are called normal modes. And we can combine these normal modes in such a way to describe the full motion of a system. So the pitches of a guitar string, for example. We can actually think of the Earth in the same way, except that the Earth's normal modes look a little bit different. Here are two examples. So, believe it or not, if a really big earthquake strikes, these vibrations across the entire planet will be triggered, and they'll be deforming like this for days. Of course, the animation is a little bit exaggerated. Obviously, they're much subtler than this, but these are the subtle vibrations I'm talking about. And so what we want to do is apply normal mode theory to the work, to a much more complicated Earth. And so really, when I described that theory in that historical slide, it really stopped here. This is what would be the deformation of a solid sphere, except that we know the Earth is a lot more complicated, right? What if the sphere is layered? What if it rotates? Turns out if the Earth rotates, the Earth flattens. So the Earth's equator is wider than its poles. So we've got to deal with that in our theory. Turns out it's heterogeneous on the inside because of the LVPs, right? We know from these CAT scans that we have a really heterogeneous mantle. So we have to deal with that in our theory. And so this actually breaks certain spherical symmetries in the equations, right? And also it dissipates energy. And what this actually means is that this tidal bulge that we get lags behind the moon slightly. And so once we've done all of that theory, what do we see? Okay, this is the results of the theory. Here's a simulation of that vertical displacement of the Earth when you have a moon pulling on it, right? And this simulation on the left here is an Earth in which I've put in that LLVP structure, so those big domes in the mantle. And this is on the right is a structure without. And they look exactly the same, right? We go up and down about 40 centimeters a day. But if you take the difference between the two, you see sub-millimeter level differences, right? And fortunately enough, that GPS study saw these differences. And it really took the most kind of sophisticated technology in the GPS and decades of those GPS stations being just stood out there, making measurements to get to that sub-millimeter level precision that we can finally use as theoreticians like myself. And so this is what we see. And so if you guys are getting ready to go to sleep, this will send you to sleep. It's very mesmerizing, but this is what you'd expect with time, right? So as the Earth rotates in a day, we're going to go up and down twice a day by several centimeters, right? And this is the difference that we're looking at when we think of those LVPs. And so I'm coming right to the end. This is my result. And so really the best fitting map of deep mantle density from that GPS data is shown here, right? So after applying all that data, this is the map of density in the deepest part of the mantle. Remember those LVPs, there's one beneath the Pacific and one beneath Africa, and here they're highlighted in red. And so what does red mean? Here on this color bar scale, red means that these regions are denser than average. So these are heavy structures, right? And so if they're denser than average, these are no longer kind of regions of upwellings because they're too heavy, right? It means that in order to get that denser material, there has to be a dense composition. And so really what we think these structures are structures that are enriched in iron, because iron is a really heavy, but also very common element in the mantle. And what this also provides is a mechanism to stably preserve these structures on that kind of billions of years timescale, which you remember at the start of the talk, those ocean island basalts that showed certain kind of evidence for really, really old structure that has only just made its way to the surface. These structures being dense and average provide a real ideal mechanism to kind of sequester that material for billions of years, right? And so just to kind of bring it back to the start, you know, we had this image of what mantle convection is like. This is kind of a very classical picture. And what we really have to do is rethink our kind of idea of what's going on in the mantle, right? We have to revise our image of these LVPs as being these kind of hot buoyant upwellings. They aren't necessarily, at least at the deepest parts, right? And what this tells us is in some ways in answering this LLVP questions that they are denser than average, we've kind of introduced a whole string of other questions concerning Earth's history and ongoing evolution, right? What are the implications of this for Earth's evolution, right? And so I'm just going to end it. Actually, many questions remain about this. What I'll do just before I end is just thank some really key collaborators of mine and key colleagues and my funders, UC Berkeley and NASA. And again, thank you all for turning out and listening to me speak, and thank Science at Cal for an excellent event.
Thank you. Thank you so much. That was wonderful. We did get an amazing round of questions in the chat, so we are ready to ask them. Somebody just asked, and I would like to say, because I didn't previously, that this event is being recorded and it will be shared with all of our Science at Cal community. It'll head out on our newsletter. If you haven't joined our newsletter, please do. It'll be on our YouTube channel. Subscribe to our YouTube channel. And you will get an email for everyone who's here. You'll get an email, check your inbox. You'll get an email with the link to the video right there so that you can watch it again or share with your friends. So the fact that folks are asking for this video already, Harriet, I think that that's a good sign. And I know that there's the awkward silence of everyone being on mute, but you had me giggling throughout your entire presentation.
It's better than in lectures, because in lectures you can see people falling asleep,
Yeah.
whereas I just pretend in my head everyone's encapsulated by the 12.
No, we're definitely, you're very engaging and have nice commentary about drama queens and those sorts of things. So thank you. I'm going to ask folks, I know Jeff always has a question, and Jeff can't raise his hand. So besides Jeff, if anybody else wants to raise their hands using the reaction button, please feel free. Jeff, why don't for now, you can go ahead and ask one of your questions, and then if we get to more of them, we could do that after we get through some of the questions that people sent me in the chat. Is that okay?
Yeah, fine.
Okay,
thank you.
Great. Mm-hmm.
Well, one of them you mentioned on the last slide, but I entered this question early, and maybe you can expound on it in the last slide. What do the local heterogeneities imply for the evolution of the mantle itself, the local and also, as an adjunct to that question, there are elastic reactions of minerals in the earth, and there are plastic reactions in which the earth deforms and doesn't come back. How does the elasticity of various iron oxides depend on the depth of the iron oxides, and does the content, which iron oxides are present, vary with depth? Those are the two related questions. Thank you.
Jeff, you started me off on some difficult questions, but I appreciate it. Thanks for the question. So, right, the first question, right, so how do these affect the evolution, right? So again, this is a really simple mantle convection simulation where you only have thermal heterogeneity. So the only thing that's causing these things to rise is that they're hot. We don't have any compositional heterogeneity in here, but what these LVPs will do, because they're basically at the equator of the mantle and are so large, they really could have kind of implications for how actually kind of really long scale types of cycles in mantle convection happen. So I don't know if people are aware, but we have what's called Wilson cycles, which are essentially supercontinental cycles, right? So every few hundred millions of years, what we know in the geology is that we have the amalgamation of all the continents and they form a supercontinent. So the last one was Pangaea, right, where kind of North America, South America was stuck to Africa. If you can imagine that is really a manifestation of this large scale overturning deep from the mantle, kind of sourced from this kind of really large scale convection. These LVPs, if they're dense or if they're upwelling, will have a really big kind of consequence on things like supercontinent amalgamation and breakup. So that's kind of one example. And for your second question, it's really, really a great question. So yes, the elastic parts, I kind of skipped this detail in the talk, but yeah, the elastic parts of the mantle, so how rigid the mantle is just as important as the density of the mantle. And really, when I showed you those seismic images, what they're really showing is that kind of elastic effect. And so what we did in this analysis was assumed the elastic effect from what seismic CAT scans, those seismic tomographic images showed us. And the plastic stuff. So it just so happens that plastic deformation really needs higher levels of stress or longer timescales. And it just so happens that body tides are really tiny. So I say 40 centimeters up and down, but that's 40 centimeters on 3,000 kilometers of rock, right? So it is really tiny strain, what we call strain. So the deformation is really tiny when you really think about the entire mantle. So spread that 40 centimeters across 3,000 kilometers. And so you just don't reach the levels of deformation for which that kind of non-recoverable deformation you're talking about happens.
Thank you.
I've taken too much time on that, sorry, but great questions.
Yeah, Jeff always has the great question. So if we don't get to some of the other ones, Jeff, we'll tune back in. So if anyone else wants to ask, go ahead and raise your hand. Otherwise, I will just go into the ones that were messaged to me in the chat. So one of the questions I know very early on, you were talking about the viscosity of water versus viscosity of the mantle. How do we even know the viscosity of the mantle?
Right. Yeah, that's a good. That's really interesting because it's the other half of my research, right? And I think Dee touched on it, but one thing we want to do is understand how mantle flows. So you want to try capture observations that capture this flow. And so one thing that you may or may not know, but about 25,000 years ago, we were in the last ice age. So if you've seen those movies, that was around 25,000 years ago. And so the last ice age turns out right down to Long Island. So I don't know if people are I know there's someone calling in from New Jersey. You were covered in about 3 or 4 kilometers of ice. And that ice sheet covered the entirety of kind of Canada and most of the US. That was at its peak 25,000 years ago. It completely melted away about 8,000 years ago. But what happens is, as that ice sheet kind of existed, it completely warped the crust. We have this massive depression, right? Downward depression of the crust. Once the ice sheet disappeared, we have this delayed rebound. And it turns out Canada is still uplifting from it, right? And so one really interesting observation that you see if you go to places like Hudson Bay are strand lines. So they're kind of old ancient beaches 200 meters above sea level. How did those beaches get there? Basically, it's because Canada has just been uplifting for the last 8,000 years, right? Maybe even a little bit longer. And so if you get an age of these different beaches at different times, at different elevations, you can basically track how the Earth has uplifted, has rebounded in time. And it turns out the time scale of that rebound tells you something about the viscosity of the deep Earth. And so capturing the deformation in different ways will give us an idea of the viscosity of the Earth, but it's not easy. Observations are scarce, and kind of our idea on mantle viscosity is still, it's still uncertain. We have a big range.
Excellent. Well, that was a great question for whoever asked it, because it probably seemed like there would be an easy answer, but there never is.
No.
Right. Yes. Felipe, go ahead and unmute yourself if you can, or I can do that for you. There you go.
Yeah, sure. Thank you, Harriet. That was very interesting. I was wondering whether there are some certain normal modes that are never excited or just have never been observed to have been excited, and whether that tells us something about the structure of the Earth.
Right, great question. So Felipe is part of the EPS department, just FYI for people. Great to see you here, Felipe. Yeah, so these sort of vibrations I showed on that animation, there are some really interesting ones that are very subtly detected because they're weakly excited. So like when an earthquake strikes, they might just shake subtly. And there's a really special subset that I'm studying right now, and it's that these vibrations, there's a certain subset called Stoneleigh modes, and these are vibrations that are trapped along the core mantle boundary, right? So they're trapped here. How we see these vibrations is either by, for the body types, we have GPS stations up top, but for seismic vibrations, like these normal modes, we have seismometers at the surface. Now, if you have these vibrations that are deep and trapped along the core mantle boundary, it's really hard to measure the shaking that's caused by those modes at the surface, except now we can. They're very subtle, but we can see these modes. And so because they're shaking at the core mantle boundary, that's where they're vibrating, they're really sensitive to structure in the deepest parts of the mantle and in the core as well. And so remember those LLVPs? What a student of mine is trying to work on is exactly how these vibrations, now that we can observe them, if we can really get to grips with our theory, which is what he's working on, how we can use those observations of these really tiny signals, and how we can use them to teach us even more about these deeper structures.
That's so interesting. Thank you very much, Harriet.
Thank you.
You on campus.
Yes, I am.
So we have some questions about the size and numbers of the LLVP. So I'll try to do these few questions justice. Do you think that it's random that there are 2 on each side of the Earth, or do you think that that is evolutionary they it goes, right? The other question is that because there seems to be 2 of them, two big ones, do they then store a lot of energy because of that? If there were more LLVPs across the Earth, would there then be the same smaller energy per LLVP because the energy is spread out amongst the lots?
Oh gosh, yeah, okay, really. Actually, some of the why are there 2? That's actually a really deep question in earth science that we're tackling right now. But one thing is, I can talk to you about the scale, right? So one thing I talked about viscosity, and again, these 2 things are really tied together. So when you go deep into the mantle, what we find is the Earth gets more and more viscous. So just think about tarmac getting even more tarmacy as you go down into the depths of the planet, right? And so what does that do? Essentially, it means that tiny little kind of flickerings of upwellings and stuff, like kind of tiny small scale features, just can't exist because the Earth's so thick and viscous that you broaden all the structure, right? And so these LVPs are really just kind of a manifestation of us knowing that because of the pressure effects of rock, as you kind of like just keep squeezing rock, it's going to get stiffer and stiffer and stiffer and more viscous. And so it means that kind of spatial features of kind of different heterogeneity in the mantle will broaden. Why we have 2? That's a really good question. Some people, again, when we kind of think about the rotation of the planet, that these just happen to align at the equator is quite important. So a great analogy is that the largest volcano in the solar system is actually on Mars. It's Olympus Mons. And just so happens that Olympus Mons, for as far as we can tell, has been for a long time at the equator of Mars. And so what this actually does, if you kind of remember back to physics, it's sort of that arrangement of this kind of excess mass at the equator, so sorry, across the equator, so basically perpendicular to your rotation axis, is actually energetically quite a favorable place to be. And so why there are 2, some people think there used to be a different number, and some people think when we have a supercontinent, maybe we only have 1. So it really is kind of, we have the snapshot of what the mantle looks like today. It's an open question how that evolved back in time and how that will evolve in the future.
That is interesting because I did notice that they were both at the equator. I thought that's interesting. Right. Yes. All right, Dale Smith, do you want to unmute yourself? I know you've been asking questions in the chat too, so you're a good question asker.
Yes, I was wondering how the glacial melting around the world is affecting your studies in terms of the effect of the volcanism on the planet, because you're focusing on the equator, but the global melting is occurring on the polar regions.
Right. No, that's really interesting. Yeah. So it's kind of nice, these questions. I don't think that it was kind of planned this way, but it's touched on very different parts of my research. So glacial melting is very important. So I think Dee mentioned that I study these kind of billions of years scale processes, but in order to kind of really disentangle all these different signals that you're measuring, you also have to understand these modern day processes. So, you know, when I talked about the last ice age 25,000 years ago, that ice is gone, and it's been and gone. And the Earth is still deforming because of it, but you're right, you're completely right. We have ice sheet collapses at the at the poles, right? We have 2005 Larsen B, the size of, I don't know, some one state. They always compare it to a state, right?
I think it's Rhode Island, no?
Rhode Island, the
Yeah.
size of Rhode Island just came off the Antarctic ice shelf, right? And so what happens to the solid Earth in response to this? So just so happens right now, in terms of the kind of interesting places to kind of think about when you melt an ice sheet. So an ice sheet, if it just happens to be in a volcano, the weight of the ice sheet itself may or may not affect the volcanism that's happening. And so one really kind of hot topic place is Iceland. We know that Iceland has actually been kind of erupting a long time. People have been studying, and this is still kind of in the works, how melting the ice caps could affect that kind of volcanism. It's really the same physics about the volcanism that happens in underneath the ocean of the water. You can imagine that if we move in and out of ice ages, we're adding basically 130 meters of water into the ocean, which doesn't seem like a lot, but it's enough. But that extra weight will weigh down on the ocean floor, and those volcanoes that I talked about, that kind of string of underwater volcanoes, you're going to change the pressure at which those volcanoes exist, right? And why we get a lot of volcanism at those points is because actually the mantle starts to decompress. When you decompress the mantle, you lower its melting point. So you make it easier to melt. And the same will happen. It's the same physics, right? Except that we have ice instead of water. And so, no, this is a really interesting question, but it really is at the forefront of Earth science research, and especially touches on kind of the interaction of the climate system with the solid Earth system, which is kind of really, I really work at that interface, because we're starting to see more now that, Earth is an entire system, and we have to consider everything, every kind of subsystem, and how they talk to each other. So this is a great example of that. So thanks, Dale. That was a great question.
Yeah, and there was a second half to that question. I wonder if she was wondering if the Earth drilling, does that have any effect on surf expression, bulge, those sorts of things?
Earth drilling, not so much. So these I think like the deepest we've gotten is just a couple of miles, right? But we're really talking about the depths of the mantle, which is thousands of kilometers. Things that we know that these things do interact. That we know that there's a flurry of magnitude 3, 4, a few times 5 earthquakes, because we're pumping water into the bedrock of Oklahoma because of the fracking and stuff like that. And we know that these sorts of kind of things that we do as humans could bite back at us.
I don't know if you can hear me, but
yeah,
I wasn't talking about that. I was talking about major drilling like Panama Canal and the enlargement of the Suez Canal and other major waterway constructions for the big ocean liners. I understand that when you remove, not so much in the ocean, but when you remove soil like rock at the Panama Canal, the ground rose. And instead of just drilling across, they had to put in locks because the ground kept rising. And it was only like 400 feet in width.
Right. No, it really is. On one hand, it really is just Newton, it's gravity. When you move mass, something's going to happen, right? And to get back to equilibrium. And so, no, you're totally right. I'm trying to think of certain examples. Damming of water. Like if you kind of think about the Three Gorges, which is one of the biggest dams in the planet, that has a gravitational signal that's big enough to actually draw ocean to it. And we can measure that in the satellite data. So you're completely right, Dale, that these sorts of kind of manipulations of the land definitely kind of have measurable effects, and effects that you don't necessarily think about when you first do it, right? Until it happens and you're like, oh, darn. Right. No, it's really, I'm sorry, I misunderstood the question you asked originally.
Yeah, so did I. So thank you for clarifying, Dale. So before, I know we have some time to ask a few more questions, but before a bunch of people start jumping off to head off to dinner, I wanted to ask you, how did you even get interested in earth sciences? Maybe there's some future earth scientists in the audience, and I'd like to know, I'm sure they would as well.
Yeah, I mean, it's kind of I grew up in the UK, as you can probably hear. I was actually a music school dropout. It turns out I have stage fright, and so I had to figure something else out. But I'm fortunate enough to have family both in Texas and California. And so one time we were really able to visit. We did a road trip across Texas and California, and there's something about the vastness of America. But also, we saw the Grand Canyon, we saw White Sands and all this, and Joshua Tree, and you kind of, for me, it was kind of eye-opening because I just had never seen that kind of stuff in the UK. If you're from Europe, you definitely know that it's pretty much impossible to go anywhere without seeing the effects of civilization. Even if you're in the countryside, oh, there's a farm. Whereas if you kind of, the vastness of the US really was something that appealed to me. So I, asked my dad, what do I do if I want to kind of study this? Oh, you should try geology. And I was like, oh, great, I'll try geology. And I already alluded out, I'm useless out in the field. But it turns out geophysics marries the same too. I still get to answer these questions, but yeah, I'm completely useless at reading a map. I can do a few equations and keep myself busy that way.
So either you've gotten over your stage fright or you have no Zoom stage fright. Which is it?
It's possibly Zoom stage fright. You have to ask my students. Tomorrow is the first lecture of the semester. Well, today was the first lectures of the semester.
Yes. Well, I was surprised that you said that, because I feel like you have no stage fright whatsoever. All right. So now that I did have a question, but then you another fun one, which was, where's your coolest field site you've been to? But since you don't do field work, what's the coolest then geological structure you've been to?
Oh.
Yes. Is it the Grand Canyon?
The Grand Canyon was up there. I mean, that's a difficult one. So
that's like, I know.
I can just name any national park in the US and just be like, wow, that is quite well, a unique one was White Sands, actually. So it's in New Mexico. It's a desert of gypsum, and so it's so rare because gypsum is really soluble. So you never get gypsum deserts unless they're kind of landlocked and have no access to water. And so you're just here and it looks like snow, but it's sand, and it's baking because it's New Mexico. So that's kind of unique.
Yeah, definitely. Well, we'll have to visit that then. So how does the deformation data align with satellite measures of gravity? How does the Earth gravity vary as the Earth is deformed? Good question.
Yeah, geophysicists use the gravity data a lot. They align pretty well, and they tell you slightly different things. So that's nice. They're complementary, right? If you're measuring how the Earth deforms just in space, and how under that deformation, because you're redistributing mass, you're going to change the gravity field of the Earth. And both of those two things in combination tell you slightly different things, so you can use that to your advantage. We actually know the gravity field of the Earth pretty well, and it's really clever. We used to just, put a satellite in orbit, and that orbit will slightly perturb because as it goes across, like, an area of high mass, it's going to accelerate and then it'll slow down. And so what happens is you send light beams down and measure the height of the satellite as it goes through. Now what we do is actually we send pairs of satellites up. So we basically we have a satellite mission called GRACE, and that's now discontinued, but it lasted for decades. It was 2 satellites that kind of just in tandem, like a tandem bike, went around the Earth. And so what really changed the game with GRACE was that rather than sending light beams down, and it turns out that the Earth's atmosphere really complicates the signal a lot, right? What GRACE does is that it sends light beams in between the satellites as it traverses. So you can imagine if you go over some sort of mass high, the first satellite will speed up and then slow down as it passes it. And then the second satellite will do that. And there's a little lag behind the two. And if you measure the distance between the two, it's a lot more accurate than measuring the distance of the satellite right to the ground and back. And so what Grace did was demonstrate, and now we have.
That's why we have that.
Sorry, repeat that, please. Sorry, Dale, I missed that.
Oh, no, I think it was just her forgetting to mute. I muted. I think it's fine. Yeah.
Right. No worries. It happens. But so now we have Grace for other planets. We have Grail for the moon. It's, again, it's a pair of satellites that go around. And so, you know, I've got this NASA badge up here because NASA did fund some of this research, but a lot of this relies on these kinds of, you know, really these missions that take decades to plan, and, you know, a few administrations in a row to approve and kind of keep supporting. GPS, which I use, stemmed out of the DOE. So it was, the Department of Defense, DOD, and for a long time wasn't allowed to be used by civilians until like the 70s, I think, the mid 70s, then it was declassified. And so civilians can now use it. But again, all these different types of information, you know, I sit in my desk and just, you know, fiddle around with equations, but really to be able to make any of my work useful are these observations, and the people that kind of process the data and really take meticulous care to get that accuracy. You know, it's not easy.
No, I'm an atmospheric scientist, so we're constantly apologizing to everyone who has a satellite or a telescope for having to do corrections.
Right. Well, you have to answer a lot of questions about the weather.
Yeah, I'm always like, I'm not a meteorologist. Like, you may not know about one particular rock. Same. All right, so there's some more great questions. So this is an interesting one. Are there any remnants first of the different epochs of Earth's bombardment that you can see in the mantle? Can you see anything like that, or so much overturning?
I guess there's so much overturning, but I am trying to think about that. Like,
good question.
I'm not sure. It's a really good question. It stumped me. So for those of you who aren't familiar with early in Earth's history, there was just a time when there was just a lot of like junk in space. Mm-hmm. And, you know, you either, you know, start, you know, the entire solar system was a bunch of like dust and debris and stuff, and eventually made planets through gravitation and surface attraction. But not all of it ended up in a planet, and some of it ended up, and we have the asteroid belt as it's kind of like we use that as sort of a library for what early solar system material was. And so there was a time early in Earth's history where we were kind of bombarded by basically what was left over. I am not sure. There's a lot of kind of other contamination that you have to deal with when you look at these basalts. You know, I kind of simplify the discussion, but you've got to imagine that these basalts erupt. They also erupt through the crust. And so you've got a lot of contamination for the crust to deal with. And then eventually you get that signal. And when I say the compositions are different on the trace element level. So it's really like, if I looked at the rock, they look exactly the same. And you have to really get what, you know, mass spectrometers that really see the kind of parts per million differences in these. And it really is that level of precision that geochemists, what we call geochemists that study these compositions, explore and use to decipher these very subtle signals that tell you about mantle reservoirs.
Jeff, do you want to ask one more question? I know you had a few in the chat. Yeah,
I'm going to, thank you very much for an excellent talk, Dr. Lau.
No, thank you for coming.
I did want to impart one piece of information to you that's actually hot off the press, if you can stand the magma humor. But just yesterday, scientists, you mentioned Kilauea. Just yesterday, scientists detected a swarm of about 140 earthquakes around Kilauea. So you can Google that up.
I'm
Although
definitely
the
gonna Google
volcano
that.
itself was not erupting,
Right.
the maximum magnitude was 3.3, and most of the earthquakes were under 1. And so that was just reported yesterday. My question is, how will that affect the terrain of around the volcano, and will it make the volcano more likely to erupt? And the other thing I wanted to piggyback on that, because it's really also, I don't know if you said the scope of your studies, I don't know if it includes the inner core or not. But an interesting thing is that the inner core is not growing at a uniform, one side of the core is growing iron crystals more than the other side of the core. And so to condense my question that I asked in chat, I'll just ask the last part of the question, which is, how will that affect the magnetic field on Earth? So I wanted to know if the Kilauea earthquakes will affect Kilauea eruption eventually, and if the unequal growth in the inner core will affect the magnetic field.
Right,
Thank you.
right. No, great question. So the first one, I guess I'll have to read up on it, but it could be a chicken and egg situation. Where is it because there's something happening in the magma chamber that's causing that kind of seismicity? Because it is very low level, so magnitude 1, but most people don't report that, right? Even in California, if it's not, I think if it's below a 4, your phone won't register that there was an earthquake. But if you have the app, which everyone should get, My Shake. But then, right, so it could be that something's happening in the magma chamber that is causing that swarm. In terms of that swarm being able to affect magmatism deep in the earth, that would eventually might lead to a volcanic eruption. I am not sure. It does seem very low, but again, I'd have to read up on that. And I definitely have colleagues, if you're interested, Michael Manga in the department is a volcanologist who knows a lot about this stuff, certainly more than I do. But the inner core stuff, that is really, I think that's a discovery in the last 10 years that people have been really starting to kind of move towards a consensus. And really this came from seismological observations. So, the inner core it's like a bullseye in the mantle. I told you about all those kinds of seismic waves that pass through the earth. Very few of them will pass through the inner core, but when you get those, you take those measurements and over time, you're right that there's this idea that the inner core is kind of translating and one side of it is growing faster than the other, or it could be that actually just material is flowing to that side. And so in terms of how that affects the geodynamo, I think people are still exploring that. It's really, geodynamo modeling, while it's extremely sophisticated, is trying to model a very difficult physical phenomenon. So not only do you have, Maxwell equations that you have to solve gravity, you have to solve for like chemical differences, not just thermal. And right at this point, we don't even have ideas of when the inner core nucleated. Well, we have ideas, but they span 2.5 billion years. If you ask one geodynamicist or one paleomagnetist when the inner core nucleated, one will say 800 million years ago, which is very young. And then someone will say it's been around since 2.5 billion years. And so even those first order questions, we don't quite know yet. So this translating core is a really exciting kind of what was the frontier of that research. And it's always this kind of like, are the observations leading the theory? And for a lot of earth science, it is the observations that lead the theory. And geophysicists like me, we're really simple people, like can't figure out how to explain these things, but it gives us food for thought.
Thank you. And thank you for an excellent talk.
Thanks.
Yes. We'll have to have Michael Manga back soon because he hasn't given a lecture in a while. And, I was just thinking as I was watching your presentation that although I've taken so many earth science classes, I can see how far the field has come since I haven't been taking earth science. I mean, the research, even just thinking about the geodynamo, I mean, all of these things are just moving so quickly. We're learning so much so fast. So we'll have to have you on in a few years to get an update on how things are going.
I'd be happy to come.
Yes. Isn't our crowd so great with such amazing questions that stump us and make us think?
Yes.
And
I'm going to be thinking about a few of them tonight.
yeah, and you had, I mean, and you had all the answers for us, almost all, because you had some. But I feel like that goes to show how in tune our audience is to what you were explaining, and I think that says a lot about how clear your presentation was. So I want to thank you. I want to thank those of you who joined us today, those of you who always stick around and ask those interesting questions. This is the last. Harriet, you really closed us out with a bang. We have been going 9 lectures this summer.
Wow.
And yes, and we will
Is
begin.
that earthquake humor?
Oh, yes. We could add, I should have come prepared with the puns. Yes. Because our sciences are easy to do that. But we will start again, like I said, hopefully we'll be live with some of our stay tuned, folks. We're still trying to work out how we're going to deal with Delta, but we do have our next midday science cafe third week, and I think it's the 18th. We can check on that. I shouldn't have said it if I didn't know the exact date of September with our collaboration with the Berkeley Lab, and we're going to be talking about smoke, fire, and health. So that's going to be a great one since we are in fire season. So stay tuned for more information about that. Harriet, again, thank you so much. You are fabulous. Audience, you are fabulous. Yes, and have a wonderful night, a wonderful dinner. Grab yourself a beverage, tea, or a cocktail, your choice. Good night, everyone.
Night.
Good night.